Hello and welcome back to the course on algorithms. In today's class, we will discuss dynamic programming. Dynamic programming is an important algorithm design technique. Let's start with an example. Let's start with the first problem. This problem is known as the coin exchange problem. You are given k different coins of different denominations. Problem always coins of different denominations. There are k different types of coins, and we will also assume that there are infinite number of coins of each type. We will assume that these coins are sorted in the increasing order based on the denominations, and we will also assume that the first coin has a value 1. This is to ensure that this problem always has a feasible solution. And the problem is to find a minimum number of coins that are required to pay for a given number X. Say an real life application could be that you are designing a software for an ATM machine, and when a customer comes and he wants to withdraw let us say 100 rupees, and there are different coins notes of different denominations that the ATM has, and you want to pay for the amount that the customer has entered, but you want to give him minimum number of coins. So we want, given these denominations, what is the minimum number of coins that are required to pay for n. So that's the problem. The immediate thing that comes to our mind is the greedy algorithm. So whether this greedy algorithm gives us the correct answer is the question. The greedy algorithm here is that it starts with the highest denomination coin, and if you can, if the number n is greater than um, the highest denomination coin, then we will use that coin. Otherwise, we will go to the next denomination, smaller denomination coin. So if you can pay for n using C of k minus 1, then we will use one coin. In that case, you have to pay for n minus C of k minus 5, k minus 1. In general, when you look at CFI, if CFI is greater than n, then you decrement your I. If CFI is smaller than n, then you will assume that we will pay for the ith coin, and then we will recursively find the solution for n minus CFI. This is the simple greedy algorithm, but unfortunately this does not give the correct answer all the cases. Let's look at a simple example. Let's look at the coins of denomination 1, 10 and 25, and we want to pay for 30 using minimum number of coins. If I apply the previous algorithm, so then what happens is that we will end up picking 25. So if I end up picking 25, then you have to pay for 5. So in order to pay for 5, we cannot use 10. So we cannot also use 25, and we will end up using 1. So by the greedy algorithm, we will pick one coin of value 25 and 5 coins of value 1, right. So the total number of coins that we will be using is 6. But what is the optimum? Instead of picking the maximum denomination coin, we can pay using the coin of denomination 10. So you can pay for 30 using 3 coins of value 10, right. So this makes it 30. So greedy uses 6 coins, but the optimum actually uses only 3 coins. So let's look at another example for the greedy. So let's say that we want to use coins that are given to us are 1, 7 and 10, and we want to pay for 14. So by the greedy algorithm, the first coin that we are going to pick is 10. After that, we have to pay for 4. In order to pay for 4, you can't use the coin of denomination 10. You can't also use the coin of value 7. So you had to use 4 coins of value 1, right. So 1 into 4. So this will use 1 coin of value 10 and 4 coins of value 1. So the number of coins that we will use by the greedy algorithm is 5. But you see that instead of using the 10, if you start with the 7, then 7 into 2 is 14. Just using 2 coins of value 7, you can pay for 14. So, these two examples indicate that the greedy algorithm will not actually compute the correct answer in all the cases. So, this is simple greedy algorithm, but unfortunately this won't give the optimum in all the cases. So, this is where we use a technique called dynamic programming. Dynamic programming is a technique introduced way back in 1950 by Bellman in the context of optimizing control systems. It's a technique for solving problems with overlapping subproblems. Most often subproblems are recursive calls to several instances of the simpler problem of the same type. So in order to solve a problem of bigger size, we recursively solve the problem of smaller size and try to construct the solution to the bigger overlapping sub problem. So, so we will see with this example, and we will see more example to understand what this technique actually means. So once you design this algorithm for dynamic programming, in most of the cases, as in the case of greedy algorithms, these algorithms are easy to implement, and analyzing these algorithms for complexity and for the time and space complexity also are relatively easy. So, in all the dynamic programming problems, we will be defining what is known as a state of a dynamic programming. In this case, I want to define a table, right? So, which I will call it as T of I comma j. This is the two-dimensional table. What I want to store in the two-dimensional table of T of I comma j, the minimum number of coins required to pay for j using only the first I coins, right. So, we will build a table, this definition we are going to call it as state of the dynamic programming. We have to first decide how many dimensions are there, and in the table how are you going to, what are we going to store. In this example, we are defining T of I comma j to be the minimum number of coins required to pay for j using only the first I coins. So, this is a table of size n cross k, and so T of n comma k will give us the sorry, T of k comma n will give us the final answer, right, because we have k coins to use, we are allowed to use all the k coins, and we want to pay for n, right. So, the answer that we are looking for is T of k comma n. So, the way we build the table is by induction. We will try to solve the problem for smaller values of I and j and try to construct the table for bigger values of I comma j. Let us look at the base cases. T of 0 comma j, 0 means that remember that the denominations are indexed from I is equal to 0 to k minus 1. So, the first coin has a value of 1. So, if you want to pay for j using coins of denomination 1, then only 1, then you have to pay j coins, right. For every j, if I am allowed to use only coins of value 1, then the number of coins that I need to pay for j is exactly equal to j. So, for every value of j, if I is 0, then T of 0 comma I is j, and if the j is 0, that means that if I have to pay for value 0, then it does not matter how many coins that I have, how many coins that I can use, T of I comma 0 is always going to be 0. Let us stare at the ith coin. So, what we want to do is that we want to pay for j using the first I coins. Now, since I have the ith coin, I can either decide to pay using the ith coin, or I can decide not to use the ith coin. We have two options with the ith coin. Let us say that let us consider what happens if I decide to pick the ith coin. If I decide to pick the ith coin, in the future iteration I can still use the ith coin in the future iterations. Since I have picked the ith iteration, so I will be paying for C of I. In the future iterations, instead of paying for j, I should be paying for j minus C of I. So, if I pick the ith coin, then in the future iteration I can still use the ith coin, but I have to pay for j minus C of I, because the value of the ith coin is C of I. So, if I have to pay for j, if I already use the ith coin, then in the future iterations you have to pay recursively j minus C of I. If I decided not to pick the jth coin, then in future I will not be picking the jth coin. So, what I will be doing is that I have to pay for j using the first I minus 1 coins. So, if I decided not to pick the jth coin, then I have to pay for the entire j using the first I minus 1 coins. Okay. So, we have two options given I coin. We are trying to fill the table which is the T of I comma j, which is equal to the minimum number of coins that are required to pay for I pay for j using the first I coins. So, we look at the ith coin, we have an option either to use the ith coin or you do not use the ith coin. If I use the ith coin, then I can use the ith coin again in future iterations, but I have to pay for j minus c of I. And since I have used this one coin, so the number of coins that I will be using is T of this plus 1. And if I am not using the jth coin, then in future iterations I will not be using the ith coin. So, I will have to pay for the entire j using the first I minus 1 coins. So, I get the recursion here T of I comma j. So, I have two options since the objective is to find the minimum number of coins. Among these two options, whichever option gives me the minimum, I will choose that option, right. So, this is the minimum of two options. One is that I use the ith coin. In that case, I have to pay for j minus c of I using the first I coins. But I will be using one coins since I use the ith coin, the number of coins that I use will be 1 plus the number of coins required to pay for j minus c of I using the first I coins. If I do not use the ith coin, then I have to pay for the entire j using the first I minus 1 coins. So, the first the entire thing should be paid using the I minus 1 coins. So, the recursion that I am going to get is T of I minus 1 comma j. So, the recursion is T of I comma j is equal to minimum of T of I comma j minus C of I plus 1 or T of I minus 1 comma j. So, this is the case when I decided to use the ith coin, and this is the case when I have not used the jth coin. Let us look at an example for the one of the problem that we started with. In this case, as said earlier, T of I comma j is the minimum of T of I minus 1 comma j and 1 plus T of I comma j minus C of I. So, the first column is the indices for the I. The first one is the indices for our I. So, I goes from 1 to in this case it is 15, and so this is the j. J goes from j goes from 1 to 15 and I goes from 1 to 3. The number of coins here is k, right. So, k is 3 here. So, the T of I comma 1. So, if I am allowed to use only the first coin, this first row actually will show you the number of coins that are required to pay for I using only the first coin. So, if I have to use the only the first coin, then as the initialization side, if you have to pay for j, then you have to give j coins. So, T of 1 comma j, in this case the indexing when you write the program will be 0, but in this case it will be the value is should be actually indexing from 1 to 3 in this table, but when you write the program it will be from starting with 0. So, the T of I comma in the first row everything is j. In the second row you are allowed to use the second coin. Second coin happens to be having value 7 and the third coin has a value of 10. Now, if I have to use this condition arises only when j is greater than C of I, right. So, if I have to pay for j using the first I coins and if the value of the ith coin is greater than the what I want to pay, then you can't obviously use the ith coin. So, in this case I have to discard the ith coin and I have to pay for everything using I minus 1. So, in the previous equation when I wrote this case should be considered only when j is greater than or equal to C of I. What I have to pay for it should be greater than or equal to the value of the value of the coin that I am considering. So, with that condition, if I have the if the value of the coin is 7, then if I have to pay for 1 till 6, I can only use the first coin, I can't use the second coin. But the moment if I have to pay for j, then so this will be 1, right. So this will be 1 plus, so you have to take the minimum of two things. One is t of I minus 1 comma j. T of I minus 1 comma j will be an entry which is just above this, okay, and this will be 1 comma t of I comma 7 minus 7, which is 0. So that means that I have to pay for 0 using the first two coins. If I have to pay for 0, then the number of coins required to pay for 0 is 0. So this will be 1 plus 0. So I have to pick the minimum of 7 comma 1, which is 7. Similarly, when I come to 8, is the minimum of 8 comma, so I have to look at t of I comma 8 minus 7, which happens to be 1. So so this entry will be minimum of 8 and 1 plus t of 2 comma 1, which is 1. So the 1 plus 1 is 2. Similarly, when I come to, let's look at this example. If I have to pay for so let me write here, pay for so let's say, they say that I want to pay for 10 using the first two coins. So one option is to not to use the first coin. So if I don't use the first coin, second coin, then you have to pay everything using the first coin. In that case, the number of coins that are required is 10. If I decide to use the second coin, then I have used one coin. Then you have to pay for the remaining ones, that is you have to pay for 10 minus 7, which is 3, right. So you have to pay for 3 using the first two coins. The value of t comma 2 comma 3 is 3. So if you have to pay for 3 using the only the first the two coins is 3. So this will be 1 plus 3. So which is 4. So I will end up picking the minimum of 4 comma 10, which is 4. Similarly, when I come to 14, this is where the things will change. So if I have to pay for 14, there are two options. Either I don't use the second coin. If I don't use the second coin, then the number of coins that I have to use is 14. If I use the second coin, so I have used one coin, then I have to pay for 7, because 14 minus 7 is 7. I can use the among the first two coins, I can use the first two coins and I have to pay for 7. So the equation that I get will be t of 2 comma 7. T of 2 comma 7 has a value of 1, right. So if I decide to pick the second coin, so the equation that I get will be 1 plus 1, which is 2. Using 2 coins, I can pay for 14. So our algorithm will pick the minimum of these two options, minimum of 14 and 2. So this answer is 2. Similarly, if I have to pay for the third row, this indicates that I can use all the 3 coins. If I am allowed to use all the 3 coins, then let us say that if I want to compute t of 3 comma 10, then the one option is not to use the third coin. If I don't use the third coin, the number of coins that are required to pay for 10 is 4. And if I decided to use the third coin, the value of the coin is 10. So I will have to look at t of 3 comma 0. But if I have to pay for 0, then the number of coins used to be or 0, right. So I will end up picking the minimum of 1 comma 4, so which happens to be 1. So which essentially means that if I have to pay for 10 using the first 3 coins, then you can just use only one coin to pay for this. And so let's look at one last example. If I have to pay for 15 using the first 3 coins, this is the minimum of 3 comma, so that means that I don't use the third coin at all. So in that case, using the first 2 coins, the answer is 3. But if I decided to use the third coin, so the one coin is used, then I have to pay for 5. So if I have to pay for pay for 5 using the first 3 coins, the entry that I have to look at is this. If I have to pay for 5, then if I am allowed to use all the 3 coins also, I need 5 coins. So if I decided to pick the third coin, that is 10, whose value is 10, then the remaining 5 has to be paid using the 5 coins of type 1. So the number of coins that I will be using in that case is 1 plus 5, which is 6. So if I decided to pick the third coin, then the minimum number of coins that are required is 6. But if I don't use the third coin, then the minimum number of coins that are required is just 3. So we will end up picking the minimum of 3 and 6, which happens to be 3. So we will write 3 here. Yeah, let's understand the code for this. As I said earlier, for any I, if I have to pay for 0 amount, then the number of coins that are required is 0. And for any j, if I am allowed to use only the first coin and the value of the first coin is value 1, then the number of coins that are required is j. After that, for I is equal to 1 to k, and j is from j is equal to 1 to n plus 1. So what we are basically saying is that there are two options for me, either to use the first coin or you don't use the ith coin. If I can use the ith coin only if my j is actually greater than or equal to c of I. What I want to pay is greater than the value of the coin that I have. If that is the case, and if that is the case, I can pick this. This essentially means that picking this coin, right? So if I end up picking this coin, then I use one coin, then I have to pay for j minus c of I using the first I coins. If I am allowed to pick the jth coin, I'm picking if I am allowed to pick the ith coin, and picking the ith coin is has a value smaller than not picking the ith coin. So if I don't pick the ith coin, then I have to pay for j using the I minus 1 coins. If I'm allowed to pick the jth coin, I'm picking the option of picking the ith coin has a value which is smaller than not picking the option of not picking the ith coin. Then I am going to set t of I comma j is equal to 1 plus t of I comma j minus c of I. Because I have picked the ith coin, so the count will increase by 1, and in the next iterations I have to worry about paying for j minus c of I. If one of these conditions is not true, that means that the j value is actually smaller than c of I. That means that what I want to pay is actually smaller than the coin that I have. That means that I cannot use the ith coin, or using the ith coin is not beneficial, right? T of I minus 1 comma j itself is smaller than 1 plus I comma j minus c of I, then we will do this, right? So this corresponds to the option where I am not using the ith coin. This corresponding to the option when I am using the ith coin. So we said that we will consider two options. When I am given the ith coin, we will see whether we have to pick the ith coin. If using the ith coin gives us the minimum number of coins required, then we will use the ith coin. If that is not the case, we will use the jth coin. So the code for this has just simple if loop, and say at the end of this algorithm, if you just look at t of k minus 1 comma n, so that will give us the number of coins required to pay for minimum number of coins required to pay for n using the first k coins, right? So in the equations that I wrote, indexing is going from 1 to k, but in the programs that I have written, the indexing is going from 0 to n. So the n is still the number of coins required to pay for this, but here the indexing is going from 0 to k minus 1. So the k minus 1 coin essentially means that I am using all the k coins that are given to me. So it's easy to understand the complexity of this since there are two loops. This takes order n into k time, and since I am using a table of size order n into k, both the time and space complexity of this algorithm is order n into k. So one of the programming question here is that so I have written first the I loop, and then I have written the j loop. Can I just exchange these two loops and still get the same answer? Or is it important to write the ith loop first before I write the jth loop? So you can exchange these two loops because when I come inside, what I am looking at is the value of I minus 1 and j minus c of I. Both of these values have been already computed earlier. It does not matter the order in which you write the loop. So what I need to do is that in order to compute t of I comma j, what I need is for a value of I minus 1 and j minus e of I values. So, I minus 1 value and j minus e of I 1 value will be already have been computed essentially in the previous iterations. In other words, in the diagram that I wrote, in the table that I am writing, we have a matrix to be filled, right. So, we know how to fill the first column, we also know how to fill the first row, and the last entry, which is T of n comma k, which is the minimum number of coins required to pay for n using the first k coins. That is the answer. You can fill the row, fill this matrix either row wise or column wise. So, when you are looking at the ijth entry here, ijth entry is essentially be decided by two values. One is the I minus 1 comma j or some of the value on the left hand side. Take these two minimum of these two values and then decide the value of t of I comma j. So, you can either fill this row either row wise or column wise. In other words, the order in which you write these two I and j loops do not matter. So, now we have an order nk space and time algorithm which will compute the minimum number of coins that are required to pay for n using the first k coins. Now, we have not so now we have an efficient algorithm to compute the minimum number of coins required to pay for n using the k coins. The time complexity of the algorithm is order n into k, and we also need order n into k space. But if you want to know what are the coins that you need to pay, right? So, the algorithm so far only gives us the minimum number of coins, but if I have to find what are the coins that I need to use, can I do that using the table that I already computed? So, the technique here is called backtracking. So, what we have is that we have the table, and you know that T of k k minus 1 comma n is the minimum number of coins that are required. So, I start with I and j, two values I and j. So, I is k minus 1 and j is equal to n. Then as long as I is greater than 0. So, as long as I have more than one coins to be paid. So, what I do is that I want to check whether the ith coin has been used or not. So, this condition T of I comma j, if it is equal to T of I minus 1 comma j, that means that I did not use the ith coin, right. When I wanted to pay for j using the first I coins, if T of I comma j is equal to T of I minus 1 comma j, that means that I did not use the ith coin. If I did not use the ith coin, that means that if these two quantities are not same, that means that ith coin was used. So, D of I will keep track of the number of coins of the type I which has been used. If T of I comma j is not equal to T of I minus 1 comma j, we will remember that we have used the ith coin. Then I have to pay for j minus C of I, because this is the condition, this condition ensures that I have paid the ith coin, use the ith coin. So, if I use the ith coin, the D of I will keep track of the number of coins of the type I which I have been using. So, that count is increased by 1 and update my j is equal to j minus C of I. And if this condition is not true, that means that T of I comma j is equal to T of I minus 1 comma j. In that case, I know that I have not used the ith coin. In that case, the conclusion is that I have to pay for the j using the I minus 1 coins. In that case, I decrement the value of I. When I come out of this loop, I is going to be 0. That means that I am allowed to use only the first coin. So, if I am allowed to use only the first coin, then I know that I had to use exactly j coins. If I have to pay for j using the only the first coin, then I know that j coins are required. So, using when I go inside the loop, either j is decremented to j minus c of I, or the I is decremented by 1. So, the total amount of time that is required to find what are all the coins that I used is order n plus k. Let us quickly look at the one example of this algorithm, how this backtracking trick actually works. Yeah, let us look at this example. So, we know that t of 3 comma 15 is 3, right. So, we want to see what are the coins, what it means is that if I have to pay for 15 using the first 3 coins of type 1, 7 and 10. So what we really said is that 3 coins is the minimum number of coins that are required to pay for 15. So we are interested in knowing what are these coins that needs to be used. So the first thing that we said is that we will check whether this number is equal to the previous number, that is t of I comma j, whether it is equal to t of I minus 1 comma j. If that is the case, then we have concluded that the third coin, that is the value 10 coin, is not used. So we will the I is decremented by 1. So the next what we check is the 3 is not equal to 15. So that means that the second coin has been used. If the second coin has been used, I will not change, but the j will have to go back and check, go to 15 minus 7, which is 8. So this 3 is coming from 2 plus 1, which is 3. So we will remember that we have used one coin of denomination 7, and then we will come to 3. This entry I is still 2, I is still 1, and j is 8. This is not equal to the previous one, so again I have used another coin, but I have to go update my j to be j minus 8 minus 7, which is 1. So that's 1, right? So this is equal to 1. That means that I have to go there. So if I have to go there, so I is equal to 0 in this case. When I becomes 0, I know that I have used one coin of type 1, right? So so this table says that in order to pay for 15, I had used 3 coins. The coins that I need to use are 2 7 rupee coins and 1 rupee coin. Let's quickly do one more example. If I have to pay for 12, then again it says that I had used 3 coins. 3 is not coming from 6, right? So 3 is not equal to 6. So what I do is that so this 3 is coming from 12 minus 10, which is 2, right? So this is 2 plus 1 is 3. So I have used one coin of value 10. Then I have to pay for remaining 2 using the first 2 coins. This is equal to this. That means that I cannot use the 10th coin again, and this is equal to this. Every time when t of I comma j is equal to t of I minus 1 comma j, I decrement by j. So I come here, this implies that when I come to the first row, this implies that I had used 2 coins of value 1. So 2 coins of type 1. So I have used 1 rupee coin of 2 1 rupee coins and 10 rupee coins to pay for 12. So using this backtracking technique, we can easily see that uh, we can easily find out the number of the actual coins that are required to pay for n. So far we have seen an order nk time and space algorithm to solve the coin exchange problem. So this problem also help us to see which coins I need to use to pay for n. But can there be a better algorithm if I just want to know the minimum number of coins, right? So we can define a one-dimensional stable, so which is v of j is equal to minimum number of coins required to pay for j using the first I coins. I is not explicit here, we are not using I explicitly, but the definition is that I will be implicit when you write the program, right? So the what really happens in this case is that we will not maintain k number of rows, we will just maintain everything in one row. Cut. So let's look at this example. So if I have to maintain the v of I is initialized to v of I is equal to v of j is equal to j itself, because I'm in the first iteration I'm going to only use the first iteration. Second row, when I compute, instead of creating another row, I will overwrite the first row. So, but when I'm going into the second loop, I am assuming that implicitly I am assuming that I am considering the second type coin, and whatever answer that I get, this 15 will be overwritten with 3. The first row will be overwritten by the second row. At the end of the second iteration, so what I have is only the second because I have only one array, I will keep updating this. And finally, I have this entry. So the last entry here, v of n, will be the minimum number of coins that are required to pay for n. Since I don't have the previous columns, previous rows, I will not be able to backtrack, right? So, but if the objective is just to compute the minimum number of coins, then the one-dimensional array is good enough. Let's quickly look at how to update this particular array that I declared. right? So V of j is defined as the minimum number of coins required to pay for j using the first I coins. V of j is equal to initially j, so I'll assume that I am only allowed to use the first coin. And later on, so after that, as before, there is an implicit I here, and we are going with V of j, right? So we will try to update V of j. The assumption is that when I go inside the inner loop, I am considering the ith coin, right? So if I am allowed to use the ith coin, the condition that I am checking is whether I will use the ith coin. I will use the ith coin only if what I want to pay, that is j, is greater than c of I, and the present value of v of I, v of j. The present value of v of j that I have now did not use the ith coin. If this value is greater than 1 plus v of j minus c of I, if I use the ith coin, then I have to consider what is the minimum number of coins required to pay for j minus c of I, right? So since I use the ith coin, this will be 1 plus this. If this this essentially assumes indicates that using the jth coin, ith coin is useful when you have to pay for j. If that is the case, I update my v of j to be 1 plus v of j minus c of I. If this condition is not true, that means that I am not using the ith coin. In that case, v of j will remain the same, right? So when I come inside this loop, there is an implicit I which is sitting outside, so which is saying that should I use the ith coin or I don't use the ith coin. If it's beneficial if the minimum number of coins used to pay for j actually decreases by using the ith coin, then I update my v of j, otherwise the particular v of j is not updated. Is that the complexity of this algorithm is still order n into k, but the amount of space that we should use is only order n, right? So this algorithm is better compared to the previous algorithm in terms of the space, but time wise it's order n into k. So if you are not keen on knowing which are the coins to use, but you just want to know the minimum number of coins, then you can use this algorithm. The summary is that we have an algorithm to solve the coin exchange problem. It takes order n into k time, and the space is order n space. The summary is that the typical steps of dynamic programming is that it characterizes the structure of the optimum solution, recursively define the value for an optimum solution, compute the value of the optimum solution from in the bottom of fashion, compute an optimum solution from a already computed and stored information. The most important thing is to define the table, which we will call it as the state of the dynamic programming, and we have to decide what to store in the ijth entry, right? So this t of ijth entry in this case was the minimum number of coins that are required to pay for j using the first I coins. This we define as the state of the dynamic programming. So once I define the state of the dynamic programming, then we have to figure out how to fill the ijth entry in the table. So using the already computed values, right? So that means that you know the solution to the subproblems which have subproblems. Using the solution to the subproblems, you are trying to compute the value of t of I comma j. Once you figure out the equation for computing the value of t of I comma j using the previously computed solutions, we apply the algorithm recursively and find the t of n comma k, right? So that's the summary of dynamic programming. We have seen one example in this class. In the next class, we will come back to so what is known as 0-1 knapsack problem, and see how dynamic programming technique can be applied to solve the problem.